Welcome to our 8th lectures of flexible AC transmission system devices. We shall continue with the second lecture on the multi-level inverter. Now we are discussing about the direct current multi-level inverter and we have started discussing with the capacitor clamp multi-level inverter. Now we shall start after that. So this is a realization of the capacitor clamp multi-level inverter. Same way here we have a this diodes. You can see that there was a diode and these diodes were replaced with the capacitor, and you require to actively charge and discharge this capacitor. So this is the one of the requirements. So it should charge from this and it should discharge from it similarly. Thus what is the condition? We can see here also, if this switch is on, then this switch will be off. There is a little difference in the logic here. Previously we had S1, S2 is simultaneously on, and we generally find S1 and this one as complementary logic. Here lower switch will have a complementary logic. Similarly, these two switch will be complementary. So this is a basic difference. So here this switch, upper switch, this one and the lower switch will be complementary, and this middle switch and this switch will be complementary, and we can have a 4 combinations of the states, and we require to charge the capacitor, and so that a differentiable voltage can we get. So see that when both the capacitors, when actually you want to connect this point A to the higher end of the DC bus voltage, then both S1 and S2 should be on and S3, S4 should be off, and thus you get this voltage. Later we will find it out, this one is S1 bar. Similarly, if you wish to generate this 0, so you will connect this S1 and S3 should be on. So you will actually, then this is the realization, ultimately this is a path and this voltage comes into the picture. So this voltage is VDC and this voltage is VDC by 2, and since this voltage also VDC by 2, so you are getting a 0 voltage. Similarly, if you wish, it is quite simple, this voltage you get minus VDC by 2. Now there is a beauty of it. Generally what we do, when two lower switch is closed and you want to generate a positive voltage, a 0 voltage, then instead of the S3, S2 can be turned on. So thus this is the logic. You can see that S1, S2 and this one is S2 prime and S3 and S1 prime. So this is the way of generating voltage. So what are the takeaway of this inverter? Voltage driven redundancies can be used for having extra degree of freedom. Why? Because we have realized 0 by these two switches, S1 and S3. We can also realize these switches S2 and S4, so or S2 and S1 prime. So depending on which switching state is having a lower, you have some kind of redundancy in switching, and thus it gives more reliability and you can reduce the switching losses. Flying capacitors, flying capacitor multi-level inverter also offers output voltage waveform with the lower T state, same because number of level is high. So instantaneous error voltage is less as same in case of the direct clamp inverter, but these are the two advantages, and thereafter we come to the disadvantage. We require large number of bulky capacitor. Diodes are basically sleek devices, bulky capacitor, and we require a separate pre-charging circuits, and the controller required to be operate in such a way it charges and discharges quite effectively, and very fast charging and discharging in every window of time require very competent control circuits also. The DC capacitor voltages of the inverter vary with the inverter working conditions and depending on the which switches will on, and we require to balance the capacitor voltage always, since we have assumed that that this flying capacitor got a voltage of VDC by 2. If it is not actually, then operation will hamper, but since we use it in a closed manner, so we will ensure that this voltage gets this value. Now, another multi-level inverter is the Cascaded H-bridge. You have a H-bridge and you cascade them as many and you wish, and thus you get a Cascaded H-bridge inverter. Multi-level inverter we have discussed till now, it requires a single source, but in this case we require a separate DC sources. So, all these DC sources required to be separate, otherwise line short will take place, operation will hamper. So, what are the actually features of it? It is formed by series connection of 2 and more single phase multi-level single phase bridge inverter, H-bridge inverter. Single H-bridge converter is able to generate 3 different voltage level, that we will see little later in next slide. Each voltage leg has only 2 possible switching steps to avoid shorting of the DC link voltage, and so we require to restrict it. Total 4 different switching is possible for these 2 inverter. So, you can get the number of states. So, see that how does it work? You have these switches, and when S1 and S4 is a typical conventional single phase H-bridge inverter, so you get VAN, and when you close this to upper switch in this configuration you get 0, and similarly you can have S2, S3 when shorted you get minus DC bus voltage here, and same way you can short this to lower switches, again you get 0 here, and we require to cascade both of them. So, we get a number of levels. So, for kth H bridge if it is connected, so you will get 2k plus 1 different voltage levels. So, thus this can gives us a 5 level, and where VDC is the input voltage of the single bridge configuration. So, merits, you can have such a high degree of freedom, it is modular in structures, you can add on and you can get it, enable fault tolerant operations, because you can introduce the short circuit protections any of the devices. All semiconductor will have a same blocking capability, thus uniformity. It is so effective that it is very much retrofittable. You just increase the number of level, and when voltage level change, so you can have a same inverter configured and put into the applications. So, increase the so effective to increase the output voltage level and the power, high voltage operation without switching devices in series. This is one of the, these are the few advantages of this cascade multi-level inverter. What is drawback? Each H-bridge inverter requires a separate DC voltage source, otherwise it will short the DC link voltage and it will not be able to operate properly. And high component count, because you have a 4 switches required to count. So, here have a huge number of components comes into the picture. The H-bridge uses large number of IGBT or IGCT, whatever the switches module, it has been used in practice. So, see that this is the applications of the 9 level multi-level inverter, and so it is simple to realize. So, you have 4 blocks, so 2k plus 1 it is 9 level. So, essentially you can switch it on like that, VA1, VA2, VA3, VA4, you add them in series and ultimately you get a wave very close to the sine wave. Thus, instantaneous voltage is very low, THD content is very low and it has got a modulity. So, 4 HBs is required, ultimately you add on these 4 voltages, you get 9 level, no number of redundant voltage level also possible, and structure is modular. So, this is the case of for 9 level cascade multi-level inverter. Here is a special case, we can switch in such a way, if it is allowed a plus and minus, previous case you see that you have applied only positive voltages. Thus, one combination of switching is being used and we can generate negative voltages by it and we can increase the number of switching state by it by simply the change is the controller pattern. So, you can see that you can generate plus VDC or minus VDC. So, in that way you can generate different line of voltage level. So, this is the another voltage level, ultimately this gives you by this 2 multi-level inverter can give you a 9 level. So, DC voltage sources should be of a different magnitude, modulity of the structure in this case it is lost because power handling capability of the switches will be different. So, and less number of redundant voltages because you do not have a, it is problematic to have a redundancy here, but and designing the switching pattern is also little difficult, but what it helps to increase the level with less number of cascade multi-level inverter, and it is found very much applications in case of the solar inverter. So, now let us see, we have seen the topologies, now we require to control this topology by PWM, and while doing it we require to find it out. So, what are the different kind of PWM technique, what we have studied is a bipolar and the unipolar, and what else here it is available extra, so that it can effectively generate the voltage required by the application specific voltages that will require to be generated. So, if it is a low voltage, low switching frequency, so we can go for the selective harmonic elimination, it is same what we have discussed into the 2 level inverter, and it can go to the nearest level and the nearest vector. So, this kind of application we can go and we can combine both of them, we shall see in our discussions, that is hybrid modulations, we can combine SHE and PWM, thus we can have a hybrid modulation, and we can have a carrier based PWM which we have studied into level inverter, bipolar and unipolar. You have phase shifted, level shifted and hybrid PWM. We shall see the different kind of it, and of course, you have we have already discussed 2 level SBM. Now, we will discuss about 3 level space vector modulation. So, one typical example is the phase shifted PWM, where this sign will be, we know that in case of the bipolar PWM we require only one V sin omega t, and in case of the unipolar PWM you require Vm sin omega t and minus Vm sin omega t. And here it is also essentially a bipolar unipolar PWM is you can term as a phase shifted PWM, where phase shifting is 180 degree, but here it will be different, and this is the actually the phase shift equation. Multi-level inverter with M level requires M minus 1 triangular wave. If you have a 2 level inverter, so you require one triangular carrier wave. All the triangular carrier wave have a same frequency and same peak and amplitude. Generally it is on a uniform magnitude of 1, and this phase shifted carrier wave is phase shifted by this angle phi CR. It is given by 360 minus 1, 360 by M minus 1. It is a 5 level, so basically it will be 5 minus 1, that is 4, and so it will be 90 degree phase shift, something like that. The modulating signal is usually a 3 phase signal wave with adjustable frequency and amplitude depending on the requirement of the voltage level, and it will change. So, you have a same modulating signal, and where carrier wave will be phase shifted depending on the number of level, and gate signals are generated by comparing modulating wave with the carrier wave. So, this is see the application of it. So, this is in comparisons of you can see there are many triangular waveform. So, this one it has been considered for the 3 level inverter, and thus you have a 2 carrier for a wave. So, M is basically here it is 3. So, M minus 1 is 2. So, it is 180 degree phase shifted carrier 2 carrier wave. It has been actually put into the operation with the same carrier wave. So, this stands for actually this will be the gate signal for VG1 and VG13. So, these will be the positive signals. Same way VG12 and 23 will be given by this gate signals, where this carrier wave are actually 180 degree phase shifted. This will start from here and that will start from here. Logic is same. When V sin is or the V modulating is greater than the V tri, upper switch will be on, otherwise lower switch will be on. So, similarly you get V31 and this one is complementary, and you get VG3, and ultimately you get the voltage VAN, something like this 3 level inverter. Now, what is the amplitude modulation ratio? Is same. In case of it will be Vm by Vcr, and it is same for the 2 level inverter, and Vm and Vcr are the respectively the peak amplitude of the modulating and the carrier wave. Similarly, what is MF? MF will be same FCR by MF, and this will be the ratio, and device switching frequency will be given by FCR equal to MF into FM. So, this is a multiplication of 2. So, when you are choosing a device, you should ensure that this device can sustain this switching frequency. So, what spectrum you will get? You can see that voltage spectrum in line is quite high, and it is for the 7 level cascade multi-level inverter. So, assume that actually MMF to be 20, MF to be 20, So, you have this kind of spectrum and following that. So, the harmonics of VH1 will appear as a subbands and centered at 2 mF and multiple of the 6 mF. This is in HIN, and harmonics in actually phase like AN and AB will appear in the sideband. You can see that this will be cancelled, ultimately VN will have a frequency at 6 harmonic. So, THD will be drastically reduced to the 18.8%. Similarly, so ratio if you take it, so you will find VN, that is a line voltage. So, it will be further shifted and it will be again it will be available in 6F. So, you require a very small inductor essentially to eliminate this noise or eliminate this high frequency harmonics, and this will be around 15%, and this harmonic content will be actually 6 mF plus minus 3. This is the beauty of the multi-level inverter compared to this normal 2F inverter. In unipolar inverter, you know that it is actually line voltage is here in 2F. So, here it is 6 mF. So, it is actually 3 times higher, the cut actually lower cutoff frequency is available. So, what is the advantage of the phase shifted PWM? The frequency of the dominating harmonic in the inverter output voltage represents the inverter switching frequency. So, this is one of the constraint, and inverter switching frequency is required to be quite high. So, for the 7 level multi-level inverter, so switching frequency of the inverter is 6F into FM, and due to that high value of this value, inverter switching frequency allows more harmonic in AB to be eliminated, while low value of this help you to reduce the device switching losses. So, this is the major advantage of multi-level inverter. So, for this reason it finds more application, and in fax device we can't do anything, we require to choose a multi-level inverter of high value, but moreover you get these add-ons. In general, for a M level multi-level inverter, you can generalize that switching frequency of the inverter will be M minus 1 into switching frequency of the device. So, maximum fundamental frequency and RMS can be found. So, that is basically this much max. So, it will be 1.22 VDD, and that becomes, you know, assuming that actually VDD is basically VDC by 2. So, essentially you get half of it 0.612 M minus 1 into E. So, this is the level of voltage stress available across a switch. So, what is the advantage of this phase shifted PWM? Device switching frequency is same for the all. Switch device uses and the average power handled by the each switch is same. So, there will not be any local hotspots. If some switch conducts more and some switch conduct less, then it will generate a local hotspots. Better total harmonic distortion we have seen in the previous slides, and is obtained at an output using M minus 1 times lower the frequency carrier than the inverter switching frequency. So, it will use effectively the more switching frequency, you can say. Magnitude of the voltage changes in step, and during the switch only E, and that leads to less DVDT, and that also reduces the EMI EMC problem. Now, level shifted PWM. Another PWM technique now I will discuss. So, it is a level shifted PWM. In case of the level shifted PWM, triangular carrier waves are vertically shifted, and that band occupies a continuous one. And what is how it has been occupied? An M level cascade multi-level inverter require m minus 1. So, if you have a 7 level, you require 6 triangular carrier, all having same frequency and amplitude, and automatically the phase shifted by 60 degree. An amplitude modulation index is defined in this case is by this. So, MA will be equal to Vm by Cr minus 1, which is a level. The frequency of the modulated index remains same as that of the phase shifted modulation, that will be the same, basically it is just phase shifted. So, MF by FCR by FM. Now, this is a case. So, you have 5 level. So, for this you have a 4 carrier wave. So, you can see that you can therefore phase shifted by pi by 2. So, there is a different kind of phase shifting technique. One is in phase disposition or PID. All carrier wave are in same phase. Phase opposition disposition POD. So, you will find that there is a phase opposition disposition. Here this is actually IPD. Here you will find that POD. Essentially this one and this one are the mirror image of it, and this is a shifted. And there is another method that is called alternative phase opposition disposition or APOD. So, all those has its advantage and disadvantage that require to be discussed in great details, so that to appreciate that PWM control technique for the 3 level inverter. So, let us see, and I will give some assignment based on it. This is the modulating signal and this is the carrier wave. Ultimately, you will get the different voltages depending on the when it crosses. So, when it crosses the triangular wave, so when triangular wave is less than the modulating wave, that particular switch will be on. In that logic, you are having a sequence of the voltages, and essentially this is you get a pole to the neutral voltages. Now, in this configuration, the device switching frequency is obtained by multiplying the number of getting pulses per cycle by the frequency of the modulating wave. Here duration of the each switches get reduced. The device switching frequency is not same in different H-bridge. This is one of the disadvantage, and output of the voltages of this H-bridge H1, H2, H3 all will be different. In case of this level shifted PWM, the device switching frequency is not equal to the carrier waveform, and inverter switching frequency is equal to the carrier frequency. The voltage device of the switching frequency will be this kind, here will be given by SWDV FCR 1 minus 1. Okay. Now, we are coming to the conclusions for our 8 lectures. We shall continue to the different kind of PWM technique. We have discussed only the IPOD. So, you have to discuss POD and APOD, this kind of control technique and advantage of it. And with our next class, and this is something we require to study from our next class onward, what is the advantage of this and the level shifted PWM. Thank you.